Lesson 2-3. If you looked at objectives, so I don't know if you guys ever look at those or not, but modeling higher degree polynomials with graphs. So lesson 2-1 was more of our linear quadratic. We still work with, maybe talk about quadratic a little bit, but this lesson is more looking about cubic, quartic, the higher degree functions. The ones that, if x to the third, I expect you to know kind of the basics of what it looks like. But, we'll talk about some of how it can vary. X to the fourth, I don't really expect you to know a lot about that right now. But by the end of the lesson, I want you to. So, a polynomial. We've talked about polynomials back in lesson 2-1, made up of sum and difference of individual monomial terms. These terms are written in standard form, which is descending degree. Thus, the leading coefficient will be in front and the constant term will be at the end. So did you guys catch all that? Where'd my pen go? So when we talk about polynomials, first of all, generally, we write them in standard form. And what does standard form mean? Descending degree. What do I mean by descending degree? Yeah, start at that highest power and work our way down, right? Okay, that's typical standard form. So when I ask you for leading coefficient, if you have multiple terms, that leading coefficient is going to be in the front. That leading coefficient is whatever's in front of that highest degree term. And then that will also put the constant, which remember a constant is just a number, no variable, and that would put the constant at the end. Okay, so basic little definitions there. First thing we're going to look at graphing transformations of monomial functions. So again, this goes back to your Algebra 2 days, looking at all these transformations. Describe. So when I say describe, that means I'm looking for words. Describe how to transform the graph of an appropriate monomial function, f of x equals x to the n, into the graph of the given function. Support your answer graphically, which means we're going to graph it, and compute your y-intercept as a check. So kind of three parts here that we're going to do. We're going to describe, we're going to check this graphically, and we're going to look at y-intercept. So looking at example A, g of x equals 4 times x plus 1 to the third. What is my base function here, or what we should call the parent function? What is g of x based on? X to the third, right? So we're trying to take the graph x to the third. Can you visualize what x to the third looks like? The answer I'm hoping is yes, because x to the third is that the cubic, right? That squiggle, whatever you want to call it. So we're taking x to the third. What are we going to do to x to the third? What are the pieces that are being changed here? Okay. So remember, when you multiply by something out front, it's a vertical stretch or shrink. Because 4 is a number bigger than 1, this is a vertical stretch. What else are we going to do to this x to the third? Plus 1 tells me to go where? Left one. Because when it's in with the x, yes, it's left or right, but opposite the sign. Okay, so let's put that all in words. When I put this in words, notice the first question I asked you is what was that base graph? So what graph are we doing all this to? And so, let's see, I'm going to start with the translate. I'm going to say that we're going to translate, and I'm trying to keep this on the left so I can leave room for a graph over there. So translate the graph of y equals x to the third, 1 unit left, and vertical stretch by a factor of 4. So that is our describe portion. Get your description written down. We ready to try graphing this? I'm going to sketch a set of axes right here in this open space. X-axis, Y-axis. I think I'm going to put maybe 4 tick marks each direction. Okay. Now, I'm going to start in pencil. Let's think about what do you guys know about x to the third? It's that squiggle, right? What points does y equals x to the third go through? Goes through 0, 0, yes. So I'm just putting these points in pencil because obviously I'm just trying to get my base graph. What other points does y equal x to the third go through? 1, 1, because 1 raised to the third is 1, and negative 1, because negative 1 raised to the third is negative 1. Now, you guys know better. Is it actually a straight line? No, because I don't have room on this graph, but technically what would be the next points out? 2, 8, and negative 2, negative 8. So, and again, I'm just going to kind of put this in pencil. And you don't have to do this part. This is not a required part. But that's the basic graph we're trying to adjust, right? Excuse me. We have to move it left 1. So left 1 means I'm going to take each of those dots and move them left 1. I'm not actually going to draw that in yet. Now, how do we do a vertical stretch of 4? Do you remember? Vertical stretch of 4, you need to take what and multiply it by 4? The y, because what is your vertical coordinate? Your vertical coordinate is the y. So take your y coordinate and multiply it by 4. So, for instance, this point that it was at 0, 0, now it's at negative 1, 0. The y coordinate is 0, multiply that by 4, and you're still at 0. So that point actually is going to stay. Hopefully you've realized when we do a vertical stretch, those x-axis points stay. Okay. This point was at 1, 1. Now it's at 0, 1. What's 0, 1 going to become after I stretch it by 4? 0, 4. Can you see where this one's going to be then? It was at negative 1, negative 1. Now it's at negative 2, negative 1. Vertical coordinate of negative 1, stretched by negative 4, puts me at negative 2, negative 4. Okay, can you connect those? Technically, it's what? It's moved over left 1 and stretched 4. By stretching it 4, what's happening? Elongated, right? It doesn't curve as much in the middle, it more stretches out. Okay, expectation 1 was described. We described. Expectation 2, support it graphically. Okay, and could we punch this on the calculator, check ourselves if we wanted to? Yeah, and at this level in your game, I get it. That's a good call. Okay, however, I still want you trying to think through the moves like I had you think through first. Now, how can I compute my y-intercept to check that? You guys remember how to find a y-intercept? Okay, where it crosses a y-axis. How do I find that in my equation? Plug in what? X as 0, right? Because where does a y-intercept happen? When x is 0. So for your check, I want you to find g of 0. So if I find g of 0 for times 0 plus 1 to the third. What is 4 times 0 plus 1 to the third? Well, 0 plus 1 is 1. 1 to the third is 1. Times 4 is 4. Does that check? Yeah. Okay. A y-intercept, when you're graphing, guys, y-intercepts are always something easy to check. Because it's usually very easy to put 0 in for x. I say usually. I won't say always. But that's usually a good check there. Questions? Okay, guys. Let's talk about b. H of x equals negative of x minus 2 raised to the fourth plus 5. Okay, so we've got to talk about our description here. Reflect where? Across the x-axis. If the negative were on the x, it'd reflect across the y. Since the negative's out front, it reflects across the x. Now, what is my base graph that we're reflecting? What is my parent function? X to the fourth, yes? Okay, so y equals x to the fourth is the base graph we're starting with, which I know you guys don't know necessarily what that looks like, but we'll talk about that. The negative reflects it across the x. What else can you tell me? Right 2 and up 5? Yes? Okay, let's put that in words. So I'm pretty much going to go in the order we talked about. Reflect the graph of y equals x to the fourth across the x-axis and translate, what do we say? Right 2 and up 5 units. Okay, get it down in words, and then get ready to think about a graph. As I set up my axes over here to the right, I'm going to put tick marks 5 out, which that 5 out more has to do with the vertical direction, but I'm just being consistent here. Okay, and we'll learn as we get a little bit later on in the lesson a little bit more about what x to the fourth can do and everything. But x to the third, if you have a basic x to the third graph, it's that basic squiggle, right? And we have that basic x to the third graph, that's when we have no other x terms thrown in. Just x to the third is the only power. So what we're going to talk about right here is x to the fourth. There's no other x terms thrown in, because anytime you throw in other powers of x, like an x into an x fourth, if you throw in an x cubed, x squared, x, that changes things. Changes the look of the graph. If we just have an x to the fourth, that's what we're going to base it on right now. Let's start with our basic middle points for just x to the fourth. If we plug in 0 to x to the fourth, what's my ordered pair there? 0, 0. Yes, I'm just putting my pencil graph in, my original. What if you plug in 1? 1, 1, because 1 raised to the fourth is 1. What if you plug in negative 1? Negative 1 raised to the fourth becomes a positive 1. And I'm not going to graph this room-wise, but what if you plug in 2? 2 to the 16th. What's this kind of looking like? Parabola, yes? And It does. Oh, hold on. Who knows what I last graph on this? Okay, you guys see that? There's x to the fourth. Pretty much looks like a parabola, doesn't it? However, for comparison's sake, here's x squared. So is it identical to x squared? No. Okay, x to the fourth goes up more vertically, and if we zoomed in, you can't really tell the base is wider at x to the fourth. Okay, it touches the x-axis longer. Okay, so what you're looking at here, the basic x to the fourth graph looks something like such. Ready to do the magic to it? Okay, so what's reflecting over the x-axis mean? Okay, instead of being right side up, parabola-looking thing, it's now upside down. What happens when I move it? Where are we moving it? Right 2, up 5. So think about 0, 0. Where's that going to go? Right 2, up 5. So my brain, that's my new vertex. Where are the other points in relation to that vertex? Yeah, they were originally 1 over, 1 up. But now, upside down, so it's going to be 1 over and 1 down. Okay, and that's about as precise as we're going to get there. Notice I'm trying to make it not go out as much. Okay. Oh, I should have taken x squared off. You guys really can't see. Is that kind of what we drew? Okay. Different window sizing, but okay. What was our third item we had to do? Check the y-intercept. Now, on my graph, do we know the y-intercept right now? I mean, I don't know my actual y-intercept, do I? However, can we ballpark it? Okay, I am on there. I'm still recording. Okay. I mean, we know, for instance, is my y-intercept going to be positive? No, it's going to be negative down here, yes? So let's check our y-intercept and see what happens. How do I find my y-intercept again? Put 0 in for x. Good. So it's the negative of 0 minus 2 to the fourth plus 5. Okay. 0 minus 2, negative 2. Negative 2 raised to the fourth, positive 16. The negative of 16 is now negative 16. And what is negative 16 plus 5? Negative 11. Does that make sense with what my graph's doing? Yeah. Okay. In other words, last time I knew 100% sure I could actually check it. This time, I didn't go that far. However, think about it. Originally, it was going to be what? 2 over 16 up. Would that be 2 over 16 down if we ended up at negative 11? From 5 above, it makes sense. Okay, so again, it's a good visual check. Questions on that section? Okay. Moving along into example 2. Example 2, we are going to focus on, it's graphing combinations of monomial functions. We're going to focus on what happens to an x cubed graph when you include an extra x term, and that's x to the first term. So, and the directions ask us to do several things again. Graph the polynomial function, locate its extrema and zeros, and explain how it's related to the monomials from which it is built. So the monomials which it is built is that x to the third and that x. So, First of all, it says graph, yes? Now, we can graph this by hand. We can graph it on the calculator. If we think about it, let's see, when you put in 0, you're still going to have 0, yes? What happens when you plug in 1? 2, right? What happens when you plug in -1? No? Because -1 to the third is still -1 plus -1, which is -2. You guys made me stop and think for a moment. Wait, did I have that? Okay. So as we sketch this graph, does it still look a lot like a y equals x cubed? It does. And I'll show, this is x to the third plus x. Okay. So it looks a lot like y equals x to the third, doesn't it? And it should. For comparison's sake, and I'll talk about more in a moment, the second graph is y equals x to the third. So what's different is just the origin a little bit. And so you want to put some specific points in here, you can. But it still looks like a basic y equals x to the third graph, doesn't it? Again, we'll talk about some details of that here in a moment. Let's go through the questions. Okay, so we graphed it. Locate extremas and zeros. Okay, vocab time. Extrema. Mins and maxes, right? Extrema is a word you've got to know. Okay, that's just a word you have to know. Extremas are mins and maxes. Where do I have mins and maxes here? Do I have any mins and maxes? Maybe that's a better question. Remember, a min or max is a high place or a below place, right? What's my graph doing? It's just going off to infinity. Mins and maxes would be like hills and valleys. Do I have any hills and valleys? No. So in this particular example, we're going to say no extrema. And again, I will write up here by the word extrema, min-max. Okay. The next question is zeros. Again, vocab word, we need to know what zeros are. What are zeros? Yeah, where the line crosses the x-axis. So they are my x-intercepts. What x-intercepts do I have? 0, yes? So I have a 0 at x equals 0. Okay, the last thing we're being asked to do in this problem is to explain how it is related to the monomials from which it is built. So what do we say it's built from? It's built from x to the third and x. Now, is it pretty obvious how it relates to x to the third? It looks almost identical to x to the third, doesn't it? And this will appear more on the next one, but the other piece is y equals x. And so what I want to show you here is if I just graph y equals x. I probably need to zoom in there. So y equals x is that line, yes? And I'm going to zoom in. Okay, so there is the graph in question. Y equals x to the third plus x. That was my original x to the third. And right there is y equals x. What do you notice about that blue curve there? the blue curve, does it look a lot like my red curve? Same shape, yes. What's happening, though, there by the origin? It looks a lot like, in that small section, it looks a lot like y equals x, doesn't it? Okay, so that's how these two work together. If this had been a plus 2x, the line would change, and so would my graph. Okay, so what's happening here, what we're going to write down as how is it related to these, is generally speaking, this has the shape of y equals x to the third, but at the origin, it looks a lot like, it has the same slope, let me put it that way, or same slope or shape as y equals x. Okay, so for the third part, how is it related to monomials from which it is built? I'm going to say shape is much like y equals x to the third. Near the origin, shape slash slope, if you want, is like y equals x. Okay, you guys got what you need on that one? And again, some of that sounds like a lot to you guys right now. Probably doesn't make a whole lot of sense. Once we look at this next one where it has a minus sign instead, I think you'll see the difference. So ready to look at B? So let's first, and I'm going to graph it on the calculator here in a moment, but let's first think about what it's going to look like. You put in 0. What are we going to have? 0, yes, because 0 minus 0 is 0. Okay. You put in 1. Put in 1, we're going to have 0 again, because 1 minus 1 is 0. Okay, let's go the other way. What if I put in negative 1? You put in negative 1 to the third is negative 1, minus negative 1 becomes negative 1 plus 1, which is 0. Is this making sense? You're supposed to say no there. Okay. Now, let me show you on the calculator what's happening, because I don't know about you guys, but do we really want to work with fractions to figure this out right now? Because that's what you'd have to do to see what's happening in between. Okay, so this is just what we're graphing. Is my graph actually a straight line at that point? No. And let me zoom in so you have a better visual. Now, before I zoom in, overall, does that still look like y equals x to the third? It has that same general shape, doesn't it? Starts low, goes through the origin. Now, when I zoom in, look what's actually happening. Okay, it's not a straight line, is it? It has a couple little humps there. Okay, or it has a mountain and a valley, if you prefer. And the reason for this is because we had a minus x tacked onto this one. Okay, so I'm going to draw that in right there. Whoops. Okay, do not follow my lead there because, man, I goofed that up. that's not great looking, but okay, so that's the basic graph, yes? Now we'll talk about how these shapes combine here in a moment. Let's go through the other questions first. Extrema. He says a local min and max. Over here we have some kind of max, right? Local max. Over here we have some kind of min. It says to locate. So, how am I going to locate these? Second calc. And I realize you guys probably don't have this on your calculator here, but if I do second calc, and you're welcome to do this with me, I'll start with my max. Remember how we do this? Left bound, right bound, go back to my guess. This tells me my local max. So if I do 2 or 3 decimal places, I can say what? Negative 0.58 and 0.38 for my max. So I have a max at negative 0.58, comma 0.38. Sorry, you guys can't see what I wrote there, can you? Hopefully you're listening. And I can do the same thing to find my min, yes? Pick minimum this time. Left bound. Right bound. Minimum. You guys cannot see that, can you? No surprise, though, because this graph looks pretty symmetric, does. My minimum is positive 0.58 and negative 0.38. So minimum at 0.58, comma, negative 0.38. Those are my extremas, my mins and maxes. What about zeros? Can you tell where your zeros are? Zeros are x-intercepts. They're at 0, 1, and negative 1. Okay. So zero's at x equals negative 1, 0, 1. Now, shape of the graph, and I'm running out of time. Let me graph for you. X to the third, so you can see what that looks like in comparison. And what's the other part of this graph? It's not a positive x, but it's a negative x. Watch these graph. So there's just your basic x to the third. And we're zoomed in. What's that y equals negative x doing? It's changing the shape at the origin. So I'm going to write a description similar to last time. Remind me to pick up with that tomorrow. Okay? You can start into the homework. I don't know that you can get a full real far, but you can still start into it. Okay? And it may take us 2 more days to finish these things. I knew it was going to take a while, okay?
It's not due.
No, nothing's due tomorrow. I'll probably do everything on one day, so it'll probably be at least Thursday before anything's due. And there's always a chance it could be moved to Friday. Shape is much like y equals x to the third, but near the origin, shape resembles y equals negative x.
That's 193. Because you can't read what I said. 130. No.
I was wondering when you said 139.